Afternoon. I think we should get started to keep on time reasonably. So welcome to the second half of the program. We're delighted to have Dr. Philip Fleming from Nokia Networks in North America. He's the Senior Technology Advisor, and for several decades he has led teams of researchers, advanced technologists in design and development of innovative advances in communications. And the subject of his talk will be the impact of Boole-Shannon on the communications industry.
Thank you. Thank you. Yeah, and thank you, Muriel, for giving me this opportunity, and for the audience here. This is a very unique opportunity for me to go back over my career and review, my experiences in industry and with the applications of mathematics in industry, and an opportunity to not just look at the history of technology, but also sort of the history of technology through mathematics and how it's resulted in these new industries coming about, and how those industries, of course, changed our lives. So first of all, when I started my career, like many young people, I started off very idealistic and just, really loved mathematics. And it seemed to be easy for me, so why not do that? So I got a PhD in mathematics, wrote a dissertation in pure math. But it seemed like the trajectory was always kind of going maybe more towards applications. In any case, I got a professorship at Case Western, and I was in the math department. And but there were these things at Bell Labs that were kind of calling my name. And to tell you the truth, one of them was a higher salary. One of them was also just the the birth of the computer age as we all saw it. I mean, you could see things were happening there that were very exciting. I had a few friends working there, so I went there. And I didn't know about STEM back then, but the question is, which letter was I going to be? Was I going to be a math person at Bell Labs, or an engineer, technologist, or a scientist, or what exactly was it? Well, and I found this cartoon that I thought was interesting, kind of connects with Shannon in a way that I don't think people have quite mentioned yet. But so I said, look, I'm good at numbers. People at Bell Labs, work with numbers, so I should be pretty good there. Well, it turns out that transition took quite a while to go from pure math to engineering, and to understand the values of engineering and the aesthetics of engineering as opposed to mathematics. But this kind of connects with Shannon, because he didn't actually lose money. So it turns out, this is a quote from Claude Shannon, he and his wife started getting into investing. And there's this quote in 1986 that they've been at it for 35 years. First couple of years, as all of us do, maybe if you have been in investing, you kind of play around, you lose some money. And he said, eventually, we switched to long-term holdings, and he earned 28% per year over a course of 35 years. So was that luck? I don't know. But the guy, everything he touched, I think, turned to gold. So this was just another thing. So when I first got to Bell Labs, I didn't know really. I knew that, I was hired because I was good at math. People told me, well, you're good at math, so you can probably read technical stuff, and we'll give you technical stuff, you read it, and then you can do things. But one of the first questions that came to me, interestingly enough, was this question of what happens if you round a number twice. So these business guys came to me, and they said, hey, we got this thing where it rounds it to the nearest dollar, and then later it rounds it to the nearest 100. So, is the average 0 or is it, positive? And of course, if you just round once, you can set it up so that the expected value is 0. But here it turns out the expected value is positive, and that was like my first win. It was like, yes, expected value is positive, so I made a contribution. I kind of earned my living for the first month or something. And that was without knowing anything, right? Just walk in the door. So the next project I worked on had to do with digital signatures of email. So the idea was, when I joined Bell Labs in, I think it was 82, I guess, we were able to send email on the same VAX 11750. If you were on the same computer, you could send email. And then shortly after that, they connected the computers, and you could send email to the computers that were connected. And then shortly after that, you could send email to everybody in Bell Labs, right? But in the beginning, there was this thing about, well, we got email, what can we do with it? We just send little ditties to each other, or can we do business using email? And so the question was, can you, digitally sign an email message, which I think we're still not doing that today, but we could. And so this is where I learned about public key cryptography. And of course, they said, well, hey, give it to Phil. He's a math guy. He can figure out this, the number theory behind it. And so we did design this. We worked with some of the guys at Bell Labs, Andrew Lisko and his team at Bell Labs. And so I got to meet some of the world-class folks over in Area 11. But the idea was, we put this together, and this is where I kind of learned about patenting in industry and how important patents are in industry. So we put together this whole patent case, and it didn't get through. Why? Because if you look at Ravesh, Shamir, and Edelman's patent, if you've ever read that patent, it is like super broad, and it essentially covered what we were doing. It almost covered like all applications of public key cryptography, which was another important lesson for me, because later there were some cases that went against that patent and said, oh, that's too broad, and their original invention didn't cover it. So that was an important learning. Then I worked on optical character recognition, which is, again, something that kind of leads into AI. Again, I taught myself statistics, which as Muriel and I were discussing, when I was a math graduate student, I basically covered 3 of the 4 areas in math: algebra, analysis, and topology. I did not study probability except for a few classes. And probability was exactly the thing that I needed when I walked in the door at Bell Labs. So this gave me this first kind of opportunity. Kurzweil had a machine at that time to do optical character. Bell Labs wanted to put all their documents through and digitize all of them. So this is one of the early digitization projects. So that was important, and started me down the path of really working on statistics and applied probability in general. Then the game of Go comes in here, and it comes back later, right? So it turns out the guy who hired me, my boss, liked to play Go. And then we found this out, I don't know, about day 2 or day 3. And so occasionally at lunch hour, he'd come into my office. We had offices in Bell Labs, right? And he would close the door, and we'd pull out the Go board and we'd play Go at lunch. Now, I don't know how many of you know about Bell Labs, but this game was actually pretty popular at Bell Labs back in this time frame in the 80s. And I found myself playing a game of Go at Murray Hill with a fellow. And the game went on and on. It's 1:30, it's 2 o'clock, Anyway, we finally end. I can't remember who won, but I shake hands with the fellow, and then, he introduces himself. Turns out he's a Nobel Prize winner. So, here I am playing Go with a Nobel Prize winner. So that was important. I didn't realize how important it was until just last week, when it has now become, a giant milestone in artificial intelligence. The other thing I discovered was graphics on this Tektronix terminal. Turns out there was this really fancy Tektronix terminal that nobody knew how to use. And so I said, like, where's the manual for this? And start reading the manual. And, you know, when you have to hand plot things versus you can program a computer to plot things, that was huge, right? So, and then the last thing was computer performance analysis, which is actually what I was hired to do. Didn't know anything about it, but in Bell Labs in those days, they hired people to do things that they had no experience with. And I think, you know, part of my talk is about that, and about how maybe that's more rare these days, right? Because, especially in computer science and communications. So back then, the reason they hired me to do computer performance analysis, even though I had absolutely no education in it, was because there weren't enough of those people being trained in the universities. And now there are, and that's a good thing. You know, but what is it that we're not training today that we could use other disciplines to come in? So it's kind of a challenge. So I've worked in a lot of areas in communications. I've worked in computer performance analysis. I've worked in the physical layer, you know, all up and down the stack. I've worked on the scheduler, packet scheduling, layer 2, and so on. So, and my sense is that sort of my lack of education, of engineering education, formal engineering, allowed me to do this. And, you know, I think it's been good for the companies that I've worked for. And it's been good for me. It's been very interesting for me to wander around in the engineering land. So here at the bottom, you know, you've got Charles Babbage and Ada Lovelace. You've got you got George Boole and Claude Shannon. They called themselves mathematicians. So if you see this video of Claude Shannon from Bell Labs, he introduces himself. He says, "I'm Claude Shannon, and I'm a mathematician at Bell Laboratories." And I watched that like 3 or 4 times, because he's really, is he an engineer or is he a mathematician? I mean, and the fact that he you know, smeared those two things together, I think, was part of his genius, in my view. And also, if you look at, you know, Turing and von Neumann and Norbert Wiener, you know, these are people who contributed fundamental things to engineering, and they were identifying themselves as mathematicians. So, so why talk about math and engineering? And as you might have guessed, the reason why I'm talking is we're celebrating, you know, 2 people who identified as mathematicians in basically, you know, one of the premier engineering schools in the world. And why is that? What's underneath that, right? What is there something we can learn from that? So one of the things I remember is that a large and prestigious engineering company said that their HR department basically came out with a mandate: you cannot hire people into engineering roles that do not have engineering degrees. Okay, so it sort of went that far, if you will. And I think we all, I think we all realize that that's probably not a good idea to put those kind of boundaries on things. And I do think the industry continues to be blindsided by innovations that come out of things that are essentially mathematical, like machine learning, for example, is in a phase right now that I believe has found some underlying structures, mathematical structures, that have not been fully exploited. And just remember, I mean, there's still a lot of transformative things that come just by people fiddling around and doing something on the weekends, you know, that they're not really paid for, like Mosaic, for example. So, so in my view, one of the really main ways that math, or the discipline of math, influences industry today is that it provides mathematical proofs. Okay, so for example, an algorithm, the correctness of an algorithm can be proven. If you write it in mathematics, in mathematical terms, you can prove it. And I'll say a little bit more about that later. Abstract algebra. So when you come up with an algebraic structure, a new algebraic structure that is easy to compute with, because after all, isn't that what mathematics is all about, right? It's all about how do we come up with methods to compute easier. So if you come up with a new algebraic structure, that generally leads to some innovations. So the examples here, coding, digital computing, Boolean algebra is an example of that. I look for those things because I think they're the forerunners of innovation and technology. Number theory, again, the RSA crypto system uses results that were thought to be interesting, but interesting to number theorists, but not necessarily applicable. And when Ravesh, Shmir, and Edelman realized that they could apply this to cryptography, it was really quite astounding, I think, in the history of math. Of course, you have stochastic processes and filtering, starting with the Wiener filter and all of the huge. I mean, people didn't even think they could transmit radio signals, through empty space, and now we're getting images from Pluto, right? Just huge things like that. The power of linear algebra. Linear algebra is such a, when you first see it, such a sort of a straightforward construct. It's like you think, why am I taking a class in linear algebra? But it's such a powerful thing, leading to MIMO and network coding. You got probability and statistical signal processing, leading to digital radio receivers, pattern recognition, and then eventually machine learning. And then there's utility optimization. And utility optimization is just key in wireless these days, because the idea is to share the wireless channel among many users. How do you do this in a fair way, which is also spectrally efficient? So there's a way to do it in a spectrally efficient way that's not fair. We know that. There's a way to do it fairly, but not spectrally efficient. But how do you balance these two? Well, it turns out that this utility theory is exactly what is needed for that. So just to kind of reiterate these themes, if you look at this baseball player, I apologize if you don't know baseball, but you don't really have to know baseball to know what this man is doing, right? He's trying to hit the baseball as far as he can. What is he doing? He's standing on a solid foundation, right? And he's pushing off, okay? If engineers and scientists don't have that solid foundation that a mathematical proof gives you, very difficult to push off. Not that you can't push off from mushy stuff, because people do it, but if you have that solid foundation, Boolean algebra, you've got Shannon's information theory, you've got algebraic structures for coding, you can push off and you can write algorithms and you can write software and so on. So, and with public key, the same kind of thing. You can make it, it's provably secure. So you basically know how many operations the existing methods for cracking these things will take, right? And so that allows things like e-commerce to happen. I mean, imagine the web without e-commerce. I mean, it doesn't happen, basically. It becomes something where it becomes Twitter. That's what it becomes. Which is not so bad, but So I don't know if previous speakers mentioned this, but it turns out Claude Shannon wrote the first paper on computer chess. In 1950, it was published. And he made this really interesting comment to me in there, which is that his computer program that he wrote to play chess, which he did this in the 40s, it couldn't learn. And he said, it's a problem that it can't learn. And he said, maybe one possibility is to have a higher level program which changes the terms and coefficients involved in the evaluation function depending on the results of the games the machine has played. This is exactly what DeepMind did with Computer Go. It had a higher level policy function. It had a higher level program that went in and changed the weights based on millions of games that it played. Now, I can't stop without saying something about queuing theory, which was my first go at engineering, and the queuing theory formulas, it turns out, allow you to check architectural and algorithmic concepts. So I was the person in the meeting with the computer architects who would listen to what they said, and then I would go off and I would do a model and stuff, and I would come back like a day later or a week later, and I'd say, you know what, did you know the latency will be this, or did you know that the throughput here is not sufficient to support, these functional boxes and so on. So I have experience with this, and same thing with algorithms, and same thing with even measurements. So I remember being in the lab, and I was working with this one lab guy, very very good engineer. Came back, showed me these numbers. I'm looking at it, and I just tested it against this formula. This is that the queue length is the arrival rate times the waiting time. Okay. I checked it against that, and it didn't satisfy this law. This law is extremely general. It doesn't have anything to do with Poisson processes or anything, right? And I said, you know what? I think there might be like a bug in your measurement tools or somewhere along the line. And of course, he was not happy with that, but it turned out that was true. And so this is another way I think that math happens in industry in a way that is, people can't really see this happening, right? But it's there, and it's there again because you can prove stuff in math, and you get a solid foundation. So how about in software? I'm going to kind of challenge people. An algorithm, the mathematical form of an algorithm, you can prove it's provably correct. Once you put it in software, it's no longer provably correct these days. I think this is a big challenge. This is the biggest challenge, maybe that I can see that would maybe impact industry, because the most expensive thing about LTE, the radio technology LTE, is the software. It's not the hardware anymore. The software is very expensive, and part of the reason it's expensive is because it's error prone. There's all kinds of features, there's feature interaction. They try to reuse software, and they pull it in, and they introduce bugs and so on. So this is a very, very important thing. And I think it's a big challenge, and I think it's a mathematical challenge personally. And now, as far as utility maximization goes, I had to include this cartoon because I think everybody wants a house bigger than they can afford, right? But they end up with something less than they desire. So. And let me just close out here with something about simulation, because I know that some of you are thinking, well, what about simulation? Isn't that important? Well, sure, absolutely, simulation is important. You can't do large communication systems without doing large communication system simulators, right? But maybe few people realize that these system simulators have mathematical models built into them. They have what are called what the simulation people call mathematical abstractions built in, right? That simplify and that enable you to simulate large systems. So with that, I will kind of go down this challenge list. And is there something happening in math today that we should be paying attention to that's going to disrupt things in 10 or 15 years? We've still got some Hilbert problems that aren't solved. And I kind of pick out this sphere packing one for those of you in coding. It's like, what's special about dimension 24? It's somehow the most efficient sphere packing dimension. There's some way we can use that. Machine learning. So again, I'll go back to the DeepMind program. It took 2 years to go from 0 to beating a world champion. What about paper folding? That's kind of my favorite one. I don't know if you guys know this, but there's this whole mathematics of paper folding now. Is that, is that at a point where it can get applied somewhere else? I think the Millennium Prizes were mentioned earlier. Chances are it's something that's not on anybody's list, as somebody's working in the background. What about control theory? What about combinations? So just leave you with this thought, which I know is not true, but it's just something to think about. Can you have disruptive innovation if there's no new mathematics, and vice versa? So, okay. Thank you.
Thank you, Phil, for this very stimulating talk. Any questions? Any comments? Yeah.
The paper folding triggers a memory that David Huffman, who probably wrote after Shannon the second most famous MIT MS thesis, spent the last part of his career working on paper folding. And I don't know how theoretical versus just being very talented at origami he was, but he was also interested as part of that in what he called impossible objects. That is, when can you have figures that you see a picture of in 2D, like Escher, which is impossible in 3D, and that had something to do with the paper folding as well. So I didn't realize paper folding was back in vogue.
Yeah, I think in the last 10 years there's theorems that have proven about how you can fold paper, and can't fold it this way, you can only fold it that way.
Yep. I was just wondering about the driver. So you described mathematics being the driver of industry. What do you think about the other way around?
So I think it's a driver. It's probably not the driver. I mean, the driver is necessity is the mother of invention, I guess, right? Yeah.
Industry in any way drive the mathematics?
Maybe. Yeah. I mean, I'm sure you can come up with some examples of that, but I think the other way around is just more common. Somehow math is, I feel like it's more primitive.
What do you think is the future for quantum mathematics and quantum computation?
Yeah. Well, I think the theory on that is kind of worked out in a way, right?
Can you program it?
Yeah. So now the challenge is, can you build it, right? Yeah. And unfortunately, it wasn't as easy as just, I guess what was kind of neat about the Shannon-Boole observation was that you could build it. I mean, he said, you can do it this way, and then the technology was there. There were vacuum tubes to do it. Here in quantum computation, I don't think we have the whatever the equivalent of the vacuum tube is yet, right? Somebody has to figure that out, and it's really a combination of materials and many different disciplines, I think.
Okay, well, one at the back, sorry.
Double question. The first one is the human factor and errors, like the creation of turbo code that no mathematician really saw. It was just a technician making a mistake. And the second one is about the depth of the math. You nowadays have mathematicians that are working on 11Y05 and do not understand what happens in the conference where you're talking about 11Y04 or 11Y06. And to have engineers who are going to take this and implement it, how do we do that?
Yeah, that's a good question. I'm going to do the second one first, and then I'm going to ask you to repeat the first one. So there's a lot of mathematicians that are working on on mathematics that's about math, right? It's just math that's about math. So if if those mathematicians were to think about something in the engineering area the way that Shannon did, they may be able to use those structures that they're so familiar with applied to math itself to come up with new technology, right? I mean, that's kind of what I'm saying. As long as the mathematicians' focus and their topic that they're interested in is math itself, which is probably 98 or 99% of mathematicians who are in sort of pure math departments, that connection won't be made. So I think, but what, sort of my point is that when a mathematician comes up with a new structure, if that bubbles up into, sort of a more popular domain, it can be picked up and, inspire some technology. Now, your first question was, I'm sorry.
And errors?
Yeah.
How do you integrate this in math? Because as I said, turbo codes were, as I know, not predicted. As far as I know, not predicted. It's just a technician who made a mistake. And the result of turbo code is huge.
I see what you mean. Yeah. Yeah, that's a good point. Yeah. Yeah, I think, Muriel and I were talking beforehand, and she was talking about how if you're trained as an engineer, you're much more likely, or you're much more comfortable with varying off the path, right? So I think that's the value maybe of the engineering education, is to look at things that are close to the theory but not exactly the theory, or be willing to inject something that you don't quite understand into the program just to see what happens, right? That has a lot of value. I would say that sometimes that's based on some solid mathematical theory underlying it, and sometimes it's not. But many times, if you have a solid theory and you sort of use that to slide into an adjacent domain, you see results.
I just wanted to mention, because we had Claude give a talk a few years ago about the inception of turbo codes. And he claimed that it's not an error. He was thinking about it as an electrical engineer, and he was thinking of decoding as a amplifier. So he was balancing amplifiers, not just coming up with something random. And of course, he had been inspired by Bataille, Georges Bataille, who had done a lot of publishing on the use of randomization, going back to what you were saying about learning about randomization in French and in obscurity, about why don't we use randomization in code, so that there was the engineer and the probability. But he claimed he was really using it as two amplifiers that you're balancing, so as a good old electrical engineer.
Okay. Yeah, thanks for that.
Okay, let's thank Phil again for a wonderful talk.
Thank you.